All right, guys. So, in order to graph polar coordinates, right now if I hit y equals, not surprisingly it says a bunch of y equals. Kind of makes sense. But what do we really need? Good. So what I need to be able to do is to somehow change how the calculator works, change its modus operandi. So I got to change the mode from rectangular to polar. So go to mode. So if you go down, we're going to talk about this one in the next few sections in a little while. I think it's the last section, chapter 8 is parametric. But let's now go over to polar. You guys all right? What happened?
So radian and polar?
You're a happy group. All right. Yeah, better keep that bad boy in radians. Okay. All right. Guys are weird. So if we hit y equals now, what shows up? Yeah. And now, let's try that last one we did, the 2 plus 2 cosine theta. So put in the 2 plus 2 cosine. And now our variable, you see why it's loaded? It's loaded with variable options. So when you hit it now, it's going to be a little theta. Okay. So now, if you hit, do me this favor. Let's make sure that we all start off with the same foot. When you hit zoom 6, I'm getting tired of screaming. So guys, when you hit zoom 6 in rectangular, it says error.
Error dim mismatch.
Oh, you've got stat stuff in there. So do me a favor, hit second, y equals.
Yeah.
See where it says stat, the plot's off?
Yeah.
Pick that one. Enter, enter.
Enter.
All right, now go back to zoom, window. I mean zoom, sorry. Bless you. So in rectangular coordinates, when you hit zoom standard, it takes you to a 10 by 10 window. It's going to do the same thing for us here. It's going to do the same thing for us here. It's just also going to have a little more information. It's going to have, we'll take a look at what the window looks like. So hit zoom 6 for me. Let's all do the same thing. Zoom 6. And that's not, don't worry, we're getting there. I just want to make sure we're all in the same place. Okay. Of course, if you don't have a calculator currently, you can't be in the same place. So just watch intently. Oh, good. So what happened? Are you okay?
I don't know how to make it hard.
Oh. If you just came in and hit mode, then you got, see 4 down, it says func.
Mm-hmm.
That's for rectangular. Pars for parametric. We want POL for polar. And then you should have a bunch of R's. So everybody's right here right now, and I agree with Anna, that's a little bit, it leaves us wanting, right? So go to window and see how much more information we got here. So theta starts at 0, and it goes up to, what's this? 2 pi, I love it. 3.14 doubled is about 6.28, blah, blah, blah. So it goes from 0 to 2 pi, which is good. That's the period of cosine, so it kind of makes sense. What do you think this theta step, and this is what I was thinking ahead a while back, we can actually control how many points the calculator plots. And if I make this too large, now just watch me, don't. So if I make this like 0.8, that's a lot bigger than 0.13 it was, then every 0.8 radians is going to plot the point. So you're going to get something funky like that. It's going to plot a point, plot another point, and connect them with the line. So you're going to get this. But if you make it, let's all make it a little bit better. Let's all make it 0.05. You guys with me? Theta step 0.05. It's going to be a little bit finer. It's better resolution. Okay, very hopeful I am. Okay? Something else that's kind of wrong with this, looking back at the graph real quick, is it's a little too small. And I don't know if you guys remember, the most it gets is 4 over here, right? Remember that? The 4 out here? So maybe we can make x min and x max like negative 2, well, let's make it negative 4 to 4. And let's make y the same thing, negative 4 to 4. And then that effectively just zooms in a bit. There you go. I like it. Much better, right? That's basically what we got. A little better just because it's a freaking computer. Give me a break. Okay, so if I'm you, this is what I would do when I start to realize I got these R's to play with now. I just start plugging stuff in. Who has something they want to take a look at? I'm wide open to suggestions. Give me a function you want to look at.
Oh, no, I had a question.
Oh. I was all excited. What's up?
Right here it says pi 4 and pi 6 and whatnot. How do we compare this?
Same way. Now, unfortunately, the TI does not set up for us the circles, the scale, the polar scale. So that's too bad. But it's the same exact way. It gives us 0 and pi over 2 and 3 pi over 2 and pi. That's all it gives us, though. It doesn't fill in the circles for us. It doesn't give us the intermediate angles. But it still is there. It's just not denoted for us.
Oh, like, let me see.
Right? So on this paper, what's missing on there, on the graph, compared to this paper is the lines coming out, the radial lines, right? It doesn't have that. But it's the same exact thing. You can think about laying, I cleared it. Think about laying that polar surface on top of it with lines going out. It's the same exact thing. You can still compare shapes. That's what I'm trying to say. So if you do something you want to see if you got it right, put it in there. You can see if the shape is right. So I don't know. Here's one I'll give you.
How do you put the R's to make it like the 3 R cosine theta?
So let me ask you this.
Oh, no.
Yeah. It started off as 3 cosine theta. So obviously, just like, can I graph every single possible expression in the graphing calculator directly? Can you graph a circle when you have it in rectangular coordinates? Can you graph a circle?
Yes.
Yes, you can, but what does it take? 2 inputs, the top part and the bottom part. So if I cannot solve an equation for R, it's not like a function. If I can solve it for Y, it's a function. If I can solve it for R, it's a function. R is a function of theta then. You guys kind of with me? So if I had R on both sides and I can't get R alone, I cannot graph it on there directly. I might be able to graph parts of it. The same exact thing that happens with Y and X. I can't graph a circle directly. I have to break it up into 2 parts. Because the circle is not a function. It is now, exactly. In terms of R and theta, it's a function. So let's try this. Let's try 3 cosine 8 theta. Let's not do let's go 4 theta first. Let's not go crazy. So 3 cosine 4 theta. Try 3 cosine 4 theta.
What the heck was that? Oh, it's a flower. It's a pretty flower.
Now, I want you to notice something that will help you out in your work. And here's actually a really good idea. The higher the resolution I make it, what's going to happen with how long I've got to wait for it to complete? Longer. So, something to really help you out in your homework. Here's the finished product. Did you notice what was happening as I was going? It's going from 0 to 2 pi. So you can actually follow the outputs as it's going. It would be exactly the way we would graph it, the way that we were doing it earlier. So if I make my resolution, go to Window, make my resolution really good, 0.0, let's just try 0.1 for now. Let's see what that does. And then hit graph. It should take a little bit longer. It should go a little bit slower. Does everybody understand that? Because now at every 0.01 radian is going to calculate it and plot a point. Calculate, plot a point. So it's plotting 5 times more points than it was before. So now if I hit graph, there we go. So that's 0, and there's pi over 2, and so forth. Maybe. Until finally it hits, well, let's see, it's taking a while. So it's really nice that you can follow, as it's going from 0 to 2 pi, you can follow what it's doing. And finally it gets back to 2 pi. Cool. So there are a lot of, in the middle of this problem, you can see, if you had to do this problem by hand, there would be a lot of negative r's, possibly, because it kind of keeps going back on itself. There would be some negative r's, so you have to turn to face somewhere and go backwards. I mean, you can see that happening as this thing plots it out. If I try to trace, I can try to trace. Oh yeah, it's going to take a while because it's 0.01. So you can see the angle. Now, of course, the angle is going to be in radians. Let me see if I can get somewhere you guys can. Let's see the very outer tip of this thing. It's about 0.75 or so, right? Somebody help me out. 0.75 in degrees. How do you convert that? What's? Yeah, 0.75. So 3/4 of 180 is 45 times 3. I don't know. Help me out.
135.
Yeah, so 0.75 times 180 divided by pi, right? So what's that come out to be?
42.97.
All right, so I'm almost at 45 degrees. And in fact, it probably is 45 degrees out there. So as you see, now I want you with me. This is kind of going back to, I think, Freddie, you were asking this earlier. This is roughly 45 degrees. And you can see this is what I was saying. It must be a negative r then. I'm facing 45 degrees and I'm going back to plot this point. You guys with me? We're in the same room as you, Jeff. But, all right. And then you just keep following along. You go crazy. Now, and again, let me just show you. This one's a little bit better for this. If you make your theta step a little too crude, not fine enough, too coarse, then you get this.
I like that one better.
All right. Thought you guys might like that. That, unfortunately, is known as the wrong answer. And I hope you understand why that is. I mean, whenever this thing has some sharp turns to it, and it's not calculating enough points, it's not gonna get all the way around the curve. It's gonna go here, and it's gonna make a line straight. And that's when you get all this weird doodle crap. But if you make it a little bit finer, that's when you manage to get all the little leaves in there. Okay. So how many leaves are there? 8, which is how related to my function. 2 times 4. So if I put a 2 there, how many leaves would I expect there to be? 4. Let's see. 1, 2, 3, 4. Sweet. Now, what if I put a 3 there? 6. Ah, freaky. Now look, you can see. Can you guys see it? Yeah. What did it do? Yeah. So it seems like the even multiples of theta give enough room for it to have more leaves in the middle. Odd multiples of theta don't. They kind of overlap. So how long did it actually take for this to completely finish graphing this picture?
6.
Yeah, 0 to pi, not 2 pi. The minute I got to pi, it retraced it. You with me? So it's like the circle we did. The minute we got to pi, it would just kind of retrace itself. All right. Maybe. Yes?
Is that thing with the even and odd petals, is that the same for sine and cosine?
Oh, yeah, same thing. So, wait. I got to remember. Let's try a sine one out here. Let's try sine 4 theta. Let's start off the same way we had before. Now, notice what's the one thing that's different here? It's almost the same picture, except remember cosine was was actually centered on the axis and then offset. This is not centered on the axis at all, right? It's just kind of taking cosines and rotating it. And why does that make sense? Because sine and cosine are offset by 90 degrees. So it kind of makes sense that a lot of these would, if it's a sine thing versus a cosine, it's just going to rotate it. Like a sine circles around the y and a cosine circles around the x. Okay. So, incredibly enough, if I put a, let's go crazy. If I put 11 in there, that's an odd number. So how many should there be? 11. Let's see what happens. Oh, yeah. You can count that if you want to. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Crazy. All right, how are we doing so far? Okay. So, let me give you a couple other important ones. If you look on page 532, or 552, sorry. This one here, let's try this. 1 minus, let's see what I want to do. Let's do 1 plus 3. Let's do sine theta. Cool. I like that. And just these little stick arms down here. Yo. Sorry. So 1 plus 3 sine theta. Sounds kind of nice. It's got a little circle inside of a circle. Not quite a circle, but still. The difference, remember when we did the cardioid earlier? It was 2 plus 2. So if I make these the same, if I made this 3, then it's going to become a cardioid, which doesn't have an interior circle. It just kind of, well, of course it's huge. It doesn't actually go into itself. Oh, yes. That's what I was waiting for. Let's get away from that. I love you guys. Now, if I make, what did I have? I just had 1 plus 3 right earlier.
Yeah.
Let's make this 5 plus 3. Let's make that one bigger. Of course, now my window needs to change. Whoa. Let's change my window. I need to be able to see out. Let's go out to negative 8 to 8. Negative 8 to 8. Let's see what that does. Of course, I'm thinking about 5 plus 3 is 8, so that should have been good enough to capture everybody. So that's becoming, it's getting closer and closer to being just a true circle. It's still footballish at the moment. Okay. And then if you're looking on page 552, you can see the roses. We were just doing the roses. And they have the little rule. N, if n is odd, there's n leaves. If n is even, there's twice that many leaves. Just because of the way that it fits in. And the last little one is called a lemniscate. Lemniscate. Very at the bottom of page 552, in the little table of types of things. So if we had just cosine, let's make it, what's my scale right now, 8? Let's make it 6 cosine 2 theta. Oh, sorry. I left off one little thing. Insert a square root. Now this is going to be a good example of one that's, you can't get the full thing. I'm going to get the positive part of this. And positive, of course, in one sense. And the negative would probably just fill in. It's really hard to see on my the window I chose. Does everybody get this here?
Yep.
All right, let's blow it up a little bit. Let's make that 6, turn that 6 into a 16. So what's going on in here? Do you see how it kind of breaks up in here? I can't remember my step now. If I make my step a little better, it might be able to handle that a little better. Let's see if it does. So from 0.05, I'm making my step become 0.01. So the resolution is a little better. Of course, that's going to take forever now. Great. There you go. So you see how it's not having the same problem with big gaps in the graph? It's because whenever it goes really quickly in some direction, then if I make too big of a step in my inputs, I'm going to miss outputs. That's the bottom line. So this happens to have a pretty steep slope right towards the middle. So if I have too big of a step between my inputs, I'm going to miss some outputs. So that's not the most exciting one, certainly, but it exists. Okay. And you could just play around. What to me would be interesting, like, let's take a look at cosine of theta divided by 2. We've looked at straight up multiples of theta. Let's look at fractional multiples, theta divided by 2. Oh, my step is crappy. Why don't you go back a second? Oh, it doesn't work on this. Oh, there you go. I've crashed my
Computer.
Aw. Okay. So before you do this, make your step 0.05 again. I think that'll be fine for this. Whoa. Let me try this again. All right. Let me stop right there. So I'm going to try to do cosine of theta over 2. And actually, let's give it a bigger amplitude instead of changing the window. Let's make it 6 cosine theta over 2. Graph that thing. Now the thing you don't realize, and here is where we're getting into something a little more analytical about how far should I let my inputs go so that I catch the whole picture. There's nothing there that would necessarily tell you that something's missing, but something is missing. Now if I had like half of a leaf, it's easier to tell that something's missing. If I had some leaves and then just half of the leaf, I'm like, oh crap, I didn't let my inputs go far enough. I don't want to just do from 0 to 2 pi. I'm going to have to do further. But what's really going on here, and let's not worry about the 6. Let's look at this, cosine theta over 2. I want to, somebody was asking about this earlier, I think it was you, Kelly. I want to have my inputs go as far as they need to for this to match back up again with itself. Because then what's going to happen is it's going to kind of retrace itself. So I can stop there. This has not gone far enough. What I really want to have happen is if theta is, how do I want to say this? I want to figure out how many multiples of 2 pi do I have to really go out before it kind of sits back on itself. We have an example of this on, where was it? There it is, bottom page 551. So if I say cosine of this, when is that equal to cosine of theta? Oops. I want this, I want to know how far do I have to go in my inputs until it matches back up to where it is at the beginning. So if I kind of work with this a little bit, I'll get theta over 2 plus n pi. And I want that to equal cosine of theta over 2. So this piece, when does cosine start to repeat itself? I mean, how far does cosine itself have to go? 2 pi. So what I really need is what does n have to be in order for this to be some straight up multiple of 2 pi? N has to be 2. So n equal to 2, which means that I actually have to go If n is 2, how far do I have to go? 4 pi. So let's try that. Right now, it's set to go from 0 to 6.28, blah, blah, that's 0 to 2 pi. This work tells me that I have to go 0 to 4 pi. So if I change that window, go to window, go right here, and the beautiful thing is you just put in there 4 pi. And it calculates it for you. Now if I graph now, I'll get that top half again. There we already know. But then I'll get the bottom half that I was missing, that I didn't even know I was missing. All right. And there's that crop circle. Yes, sir.
Put that in the X minimum or one
Oh, what's up? Sorry?
You should put the 4 pi on the.
No, I'll put that on theta max.
Oh, data map.
Yeah. So the funky thing, the calculator has trouble because it's obviously got a rectangular screen. It references it X and Y. That's how it knows how tall to make it, how far to go out. What we really need is theta and R. So it allows us to control X and Y, but it also has to give us control over theta. So it knows how far to sweep. Right? Maybe. In fact, I mean, think about what this really is. What's the period of this now? Careful. Here's K. K is 1/2. 2 pi divided by 1/2. 4 pi. 4 pi. All right?
Yes.
Oh, yeah. Does that always work? No. You should do this. But in this case, you can see how that kind of relates. Okay. All right. So let's try one last one of these. Let's make it a little bit funkier than this. And when I say a little bit, I mean very little bit. Let's make it 3 theta over 2.
How do you make it to move the space?
Oh, hit second, delete. That's insert. Just like on a computer. Thankfully, I was about to say typewriter, but you guys know those existed at one point? Yes.
I know how to I have one.
Yeah? Sweet. So if you hit graph now, let's take a look what this looks like. Cool. Sorry, didn't mean to yell at you. So it looks like it's a complete picture here, right? It didn't look like anything's left out, but let's verify that. We can do the same thing we just did here. That's kind of a nifty image. So I got to see if cosine theta plus, oops. So I got cosine of, what was it, 3 theta over 2? I want to know when is that equal to cosine of 3? So same thing we just did. Really just plug in a theta plus 2n pi in there. And they have this process on the bottom of the page, 551.
So where do we add that to it?
Say again? Because I want to know how far out do I really have to go before this matches up back with where it was. I want to see where do they match up again.
Also, like when it goes back to like 0.
Back to itself. So then it starts to retrace itself.
Yeah.
I don't want to have to go too far, and I want to make sure I go far enough. So I get 3 theta over 2 plus n pi again. So I want this piece. Let me make sure everybody's with me. Cosine of 3 theta over 2. There's cosine of 3 theta over 2 again. But of course, what do I add to that to make it kind of come back on itself? And again, the period of cosine is 2 pi. So I have to add 2 pi. When is this going to be a multiple of 2 pi? When n is 2. So then I'm back to the same thing. What do I need? I need 4 pi. And that's what we actually had it set on. So that's why I didn't miss anything for that one. Maybe. So this is the work you can do. So you don't have to just try a few things out before you get the whole picture. Because sometimes it'll draw something you won't even know something's missing. It looks like it's fine, when actually you're missing more leaves or you're missing something else. So if I only do this to 2 pi, what does it look like?
It looks like I don't know.
If I change the window to be just 2 pi? But when you say half of it, it's like half of it in what way? Do you know what I mean? It's not just cut in half. It's actually got a little bit on the top and a little bit on the bottom. But here, this is what I'm talking about. This is the one that's more obvious. It's kind of like, that looks like it wants to complete this leaf. So that's when I'm like, I can see I'm missing something. But we just got lucky there. Very often we won't be able to see we're missing something. Okay. So hopefully at least a couple of you guys, at some point in the next couple of days, hit that button and just start throwing stuff in there just to see. We haven't talked about tangent. I love that sense of discovery. Look at tangent theta. It's freaky as hell. And that should make sense. Tangent is not confined. Cosine and sine are confined. Because cosine and sine can't go beyond 1 or -1, right? Tangent goes to freaking infinity. So that's what the calculators having trouble with. It goes to infinity in a few different places. So of course that picture is not going to be very interesting at all. It's going to be.
How do you do sine cube?
You one way to do it. Probably the safest way to do it. You don't want to put sine. You can't just put a cube there. You have to put sine of theta, and then outside of here, cubed. Some of you guys with the newer TIs, I think you can put a little cube on the sine like we write it. But for the rest of us, sorry. There might be a little bit going on in there. All right, let's increase this to like 6.
Trying to do the same flower.
So there's sine cubed, right?
Oh, it's because we're trying to do the one in page 551, figure 12.
551. Which?
I think it's a little flame flower.
What are we looking at? Sorry.
551,
551.
figure 12.
Figure 12. Oh, that dude. So sine theta plus sine cubed. Oh, that's a cool one. Jeez.
Yeah.
So sine, what is it now? Sine theta plus sine 5 theta over 2, right? Oops, crap.
No, but it was just
Cubed, right?
Theta, what?
Oh, it's not going to be very exciting at the moment. So what I keep forgetting is I got to make my amplitude a little bit more so I can see it. So let's make the amplitude 6. That's not good.
What the heck is that? Something happened.
Well, let's look. 5 theta over 2. So I'd have to kind of go through my process again if I wanted to see how far out I really need to take it.
Let's do this.
So 5 theta over 2.
Do we have to care about the cube first?
No. Sine. And this one, no, this one has got to be.
I think it's just because you left the 6. The 6.
Oh, I only put it on the front part. Thank you. I only put it on the sign. I got to put it on this guy too. That's one thing for sure. Oh, okay.
Looks like a turkey.
That is neat. I have no idea.
And you have an extra parenthesis
Looks like
on
a
it.
signature.
I have an extra what now?
Extra parenthesis on that.
No, I got the right number.
Come on, let's do
Oh, I
that.
see where
Yeah,
Let's practice this.
looks good.
Maybe your period.
So I'm about to check.
Uh,
It looks like something's missing. This is definitely one that we don't
Yeah,
have a
right.
clue what it's supposed to look like. right? Except for the book kind of tells me, so I know I'm missing something. So again, doing this work here,
Okay, so
so I get sine 5 theta over 2 plus 5 n pi. Now the question is, what does n have to be until this is a multiple of 2?
2.
Multiple of 2 pi. Yeah, n has to be 2. So then I have to go out to 4 pi. Are you guys kind of with me? So when you do this work, all you got to do is put a theta plus 2n pi inside. Because really what you're saying is how far out, how many multiples of 2 pi do I have to go out until it matches back with itself. So if you throw that in there, then you get this here. So now this, whatever's here has to be some multiple of 2 pi. So the first time that this becomes a multiple of 2 pi, because what does n mean? Can n be any real number? No, n can be any natural number, 1, 2, 3. So the first time this is a multiple of 2 pi is when n is 2. Then it would be 10 pi. It's a multiple of 2. So I've got to go out to 2 times 2 times pi, 4 pi. Right now, my window is only going out to 2 pi. So I got to go out to 4 pi. It actually looks like an oven mitt at the moment. All right.
Well, we need to make it like up.
Yeah, I know. Let's change that. That is funkadelic. There it is. That is cool looking.
Then you have to make a Y.
Let's go. Y max can go up to maybe 12. All right, let me let that work for a while. Okay. Oh. So you cool with this stuff here?
Yeah.
Just instead of theta, plug in there theta plus 2n pi, multiple of 2 pi addition. Then you do this work. You'll always be able to find this. Whatever's left here has to be a multiple of 2 pi. So what do you make n? N equal to 1 would be 5 pi. That's not a multiple of 2 pi. N equal to 2 would be 10 pi. That's a multiple of 2 pi. What does n have to be? It has to be 2. So then go back here. What does your 0 to what? 0 to 4 pi. Cool. Yes? All the way to 4 pi, yeah. Oh, cool, it's done. That is really neat. All right.
It's really cool. You have to admit.
Takes me back to the old video games, actually. It sort of looks like a Nintendo UFO comics or something. Flower. All right. So, yeah.
I can't seem to find my data. My window settings for my graph.
Do you have the bar showing up? Do you have it in full?
I have it on forward.
It must be out of full or something. That makes sense. It won't let you control it. Maybe inspires that. If you don't have a 83 or 84 calculator, I more than likely won't be able to help me out that much, just because I haven't used them that much, if at all. Okay. Cool. So what I want to do for the rest of the time, which is not that much time, is continue going in chapter 8.
I see.
Thank you. Can you start putting out the little candles? All right, so section A3.
What about A2?
What's that? You're right.
I feel like this is like last section of 7.
H1 was polar coordinates, just points. H2 was what we just did, equations. And now H3 is going to bring in an old friend, complex numbers.
Oh, no. We don't like them. Put them in the back.
Of course, I base my curriculum on what you like. No, I don't. That's right. So we're used to, if I plot a real number, x equal to 7, that's not very exciting. 0, 1, 2, 3, 4, 7. Yeah. So what complex numbers, on one level at least, what they do is, how many parts are there to a complex number? So what's the general form of a complex number?
The real part.
Yeah, a plus bi, real part, imaginary part. All right, so one way to take care of this, and what actually leads to a really interesting way to solve something like that, just to give you a little motivation for what we're doing, because we're going to get into slightly freaky stuff. And of course, we already have, but this is even freakier. How many answers should this have? 16. There are 16 answers to this. I like it. Don't just count the 16. One of them is obviously 1. Another one is negative 1. All right, so there's 2 real answers. There's 14 more answers beyond that. So to do this by hand, who knows what you'd have to do?
Bye, and you know.
So if you factor this out, careful, x to the 8th, and this, you can go further. Now this is obviously going to have what kind of answers? How many of what kind of answer will this have? I'm sorry.
Imaginary.
Yeah, this is going to have imaginary. Why?
It's going to be a negative.
Because a real number to the 8th power is at least 0. And then imaginary 1, 2, there's no way. So this has got to have 8 complex answers. My God. This one I can go a little bit further with, and then another one I can go a little bit further with. But I'm going to keep collecting some more complex answers. So one thing that comes out of this section is what looks like something really complicated at first, but it becomes a very easy way to get all of the answers, real and complex, very quickly. You can actually write one expression for all the answers. And then if you want a specific answer, you just plug in a value for n, and you get a specific answer. So that's where we're headed.
Okay.
The first thing we do doesn't look like we're headed there at all. First thing we do is very crazy simple. If I wanted to plot 2 plus 5i, one thing we do is beyond just the real number line, we have an imaginary number line.
What's the imaginary side?
No. It's the similar idea. When I wanted to plot x plus 2y, I have to have x plus 2y equals 7. I have to have 2 directions to move in. I have to have an x direction to move in and a y direction to move in. That's something that we as humans completely made up. We completely made that up. Just because we made it up, is it not useful? No, it's useful as hell. So here we're going, well, let's try the same shit. Let's do the same thing. I've got not x's now, but real parts, and not y's, but imaginary parts. So why don't I have like an xy axis, but not that, a real and imaginary axis? So to plot 2 plus 5i is pretty simple. 2 would be here. That's the real part. 5 there. So 2 plus 5i there.
So the I always
What's
goes
that?
in the y-axis.
Yes, imaginary, real. Because, I mean, the real is already set to be this way. The real is already set. Just like the x was set to be this way. So if I wanted to throw another one in, I got to throw it on top like that. Not sure where your mind went there, but bring it back. Here, that real is already set, so if I want to throw some imaginary stuff in there, I got to throw there.
So where does it get complicated?
Huh?
Where does it get complicated?
Shut up. We don't want to get there.
One thing you should have
Wait,
faith.
based on what we
One thing you should have faith on is the fact that it will get complicated. But not yet. So look, here is the true variable for a complex number. What's used most often, and it's a little bit unfortunate that they do this. This is still two-dimensional. So the reasoning they've had behind this is probably reals are x and y. So if I have a whole separate imaginary and real kind of plane here, I want to call this z. And in a way that's unfortunate because z is its own thing. Z is the third part of a three-dimensional thing. But we just got to get over that. That's used everywhere. So this is your general complex number statement. This is known as the complex plane. I like it. So up till math 90 or 103 or 110, I can't remember where it is. Everybody exists here, and then suddenly we start talking about imaginary numbers, and now everybody exists in this whole plane. So you're in one dimension until you learn a little bit more, and then you realize, oh, imaginary numbers exist. So now you're in like a little more complicated space.
What did you call this statement?
Sorry? Well, this is a complex number.
Complex statement, you said?
This is the complex plane.
There you go. No, don't worry about it.
All right. And one symbol that we use that looks very familiar, it's not quite what it means here, is that symbol. And that, of course, when I write that, you automatically think absolute value, but it's not quite what it is. Now let me show you how it's actually, it is pretty directly related to an absolute, to what we normally consider to be an absolute value. It's really the length. It's really this length here. And we do call it the absolute value, but it doesn't look like the absolute value when we work it out. What would that length be? Let's do it a little more generally. For a plus bi, here's a, here's b. What would this length here be?
A squared, b squared?
Now, the I doesn't have to be in there because the I is this. The I is this axis. You with me?
Somebody's going to call.
The I is this axis, right? Don't forget to throw an I into that would suck because then all of a sudden you're subtracting. You shouldn't be doing that. So it truly is a length of A, and this is a length of B. This B is on the complex, on the imaginary axis, but don't throw an I on top of it also. B is purely how far up or down that axis I've gone. There's no I part to it. So what's the, and this is called the modulus. I'm not going to use that word a lot. I might say the word absolute value because this is a more general idea of absolute value. So what is it for this? All right. 4 plus 25. 20. Right? It's nothing amazing there, really, right? Okay. What we're doing is we're looking at all the implications of if you do add this axis in, what then can we do, and does that lead to us being able to do anything else? So we really want to fully explore this. I can plot that point. I can talk about how far away it is. Now what's the absolute value of -4? Let's take a step back. 4. Yeah, and if you think about it, it is this. What's this? What's A? Let me do this again. This point here, what point is that? That's the point. -4. What's the imaginary part?
0.
0. 11. So it's like, and understood this, but there's no imaginary part to it. So let's kind of do this work and see if it comes out to be the same thing. So that's -4 squared plus 0 squared. The square root of -4 squared is the absolute value of -4, which is 4. So this is just an extended idea of absolute value. Extended to numbers that have two parts to them, real parts and imaginary parts. So that's why they use the same symbol here, because it really is the same thing. Would we ever do this work for that problem? Hell no, there's a much easier way to do it because it's not this complicated. This one is, so shit, we gotta do this work. Okay, so nothing major there. Alright, so here's this. Let me see if I can make this connection for you guys. So coming back to this general A, B. And let's say this is Z, right? That's known. What is, and let's say Z has a length, let's call it R since we're used to that. Why are we used to that? Aren't we used to that? Yeah, of course we're used to that. This is the radius. R squared equals x squared plus y squared, which leads to that equation there, right?
Oh, yeah.
Okay, good. Yeah.
Are there any margins to this?
Are there what now?
Like, are there
Negative.
Oh yeah, I keep talking about the first quadrant here, but everything is true. If I would have made this negative 2 plus 5, I would have negative 2, 5. Is that what you're asking? Yeah, so you can certainly exist in those other quadrants. Okay. So somebody help me out. You know that we just came out of this. You know we're going to use this somewhere. Here's the angle that this thing resides at, right? So what is this then? And what is this? In terms of that angle and in terms of what we know about this. Don't say A, B. I like that. I like that, but it's not what I want. Be a lot more specific.
R cosine theta.
Cool, right? So that means that A is our cosine theta, B is our sine theta. You with me?
Yes, yes.
Where R is known to be the modulus of Z, the length of Z. Okay. So I really hope that some of you guys on one level, this is nothing amazing at all. We added one more axis. We can do all the same shit we did with the x and the y axis. We do all, and that's basically what we're doing. We're doing all the same shit. What this is going to lead to, though, is mathematics that makes solving like x to the 16th minus 1 easier, because of some of the simplifications we can make for powers when it's written in this form. So what I'm finally getting to is, and this is page 557, I can write this z, a plus bi. What did we say a was?
R cosine.
And b is? Yeah. I don't know which way they normally write it. Okay, they took the r out. Put it the same way they do. And that's the way I'm used to it. Right? Cool.
What is that? I, R.
Yeah, that's I.
No.
That's I. That's I. That's I. Yeah. Now the I is back in there, of course, because I'm trying to represent Z itself. Z is a complex number. It could have an I piece to it. Okay. Now again, I'm sure most of you guys are just like, okay, I don't know what the hell this is leading to. This is all very familiar stuff, used in a slightly different way. So somebody help me out. Let's do one thing here. Let's convert a complex number into that form.
Wait, but if,
Oh,
if we do the equation, the distance equation, that would be like a squared plus b squared. Wouldn't that just simplify to like either cosine or sine? I forgot. It's one of the identities.
what do you mean? Sorry. Oh, well, of course, a squared plus b squared here has to be r squared. I mean, that's by definition, right? So I think that's what you're talking about. a squared plus b squared has to be r squared. Pythagorean theorem. And sure enough, r squared cosine squared plus r squared sine squared. Take an r squared out, you get cosine squared plus sine squared is 1.
Yeah.
Yeah. Okay, good.
Cool. I got it. Thanks.
I like it. I forgot what I was doing. Oh, yeah.
Convert that.
Oh.
Wait, okay. So if I add something like 1 plus I, z is 1 plus I.
Oh, see, I made it simple.
All right, first step is, can you graph that for me? This is the real, this is the imaginary.
Yeah.
Don't worry, we'll do one in a minute. It's got a negative piece to it, just so you know that's possible. Of course, where is that? A and B are 1 and 1, so it's going to be right there. So I've got this little triangle to work with, really. So let's kind of pull that triangle out here. This is 1, this is 1. Is everybody with me? How do I get this angle? Tangent, right? Because tangent theta would have to be 1. And of course, where's tangent 1? 45 degrees, pi over 4. I like it. And some of you guys might, hopefully would realize, I mean, this is definitely 90 there, right? There's no question, because we've built it to be at 90-degree angle to each other. If that's 1, 1, what kind of triangle is this? 1, 1, no. Not equilateral. Isosceles. It's got 2 legs the same. Well, it's got to be true about those 2 angles then. They have to be equal. If that's 90 and these have to be equal, they have to be 45 degrees each to make 180, right? All right, well, there's a verification in that. So we got the theta part so far. So I can write this so far, cosine pi over 4, cosine sine pi over 4. What's the r part? And that's just finding this, of course, and that's nothing major. Square root 2. So then this 1 plus I can be written as square root of 2 times this. This takes me back. Yeah. From right here. Once I draw 1, 1, I get that triangle. And this angle that we're talking about is how far away from the x-axis I've moved. The same angle that we're used to always talking about. Are you cool with me right there? Let's do another example. I need to make sure that you're cool with me here. That's the angle we're talking about right there. Now, just to make it easier for me to see, I drew that triangle there. How long is this side? 1. 1. How do you get that last side? And how do you get that angle? I used the right trig function. So we did the angle first. The only trig function that relates what I know here would be either cotangent or tangent. And tangent we know better. Okay, so tangent theta is 1. 1 over 1. And what angle is tangent 1? Another way to say that, tangent is what over what? What angle are sine and cosine the same, so that they were reduced to 1? 45 degrees. Cool. Or, of course, right here, you just do inverse tangent of 1. I wish you wouldn't have to, but you could. Okay. Let's do another one of those real quick here. Here, you guys try this one.
Okay. I'm ready.
Yeah.
Do you have to use tangent if you use another one?
You could use another one. If we would have done this first, we could.
Whichever one you want, right?
Yeah, as long as you get this side, you can use whatever one you want.
That's where you stop.
Yeah, that's it. Yeah.
So you don't solve it?
So this, there's no solving.
Oh.
If you did this work, you would get this.
Oh.
That's all that's saying. So this is just another form of
Trying to
this.
match it.
At the end, it's got to match.
In a way.
So you can try